Okay, so in this video, I'm going to be talking about some applications of Sylow's theorem. Recall that last time I proved the second and third Sylow's theorem, and also I was talking about the Cauchy's theorem. Okay, so talking about applications now, recall that last time I classified all those groups of order PQ, where P and Q were two distinct primes, such that the smaller prime does not divide the larger prime minus 1. So we showed that there is exactly one group, that is the cyclic group of order PQ. Okay, so now let's see. So firstly, we'll talk about groups of order 12. So groups of order 12. Okay. So now, because 12 is 2 square times 3, so we have Sylow 2 subgroups of order 4 and Sylow 3 subgroups of order 3. And then, so the possibility for number of Sylow 3 subgroups is either 1 or 4. And Sylow 2 subgroups, the number of Sylow 2 subgroups can be either 1 or 3. That is easy from the third Sylow theorem. And now let's see. So we have four choices of Sylow 2 and Sylow 3 subgroups, right? Namely all those four combinations. But if it happens that the number of Sylow 2 subgroups are 3 and number of Sylow 3 subgroups are 4, then you see there is a problem, because from this you get 4 times 2, 8 elements of order 3, right? Because each group of, like, any group of order 3 has two elements of that order, right? So you get, and all those subgroups must be distinct, because either any two subgroups of order 3 either intersect only at identity or they are the same. So because here we have four distinct subgroups, we will get 4 times 2, that is 8 elements of order 3. And from each Sylow 2 subgroups, you will get uh, or or maybe you can look at it in this way, that we have already we have already got 8 elements, right? So remaining are only 4 elements, right? So remaining, there are only 4 elements in the group, because the group has 12 elements. So then any two Sylow 2 subgroups, for example, if you take this is a Sylow 2 subgroup, so here you have 3 elements of order 2 or 4, right? And there is another Sylow 2 subgroup, right? So their intersection can be identity, or let me write it in this way. Can their intersection can have order 1 or at most 2, right? But even in that case, the union will have how many elements? See, there are 4, and here you have 4, and two of them, and the intersection has two of them. So you get 6 elements, right? So, and that is a contradiction, right? Because we have already exhausted all the elements, because we got 8 elements here, and the remaining can be at most 4, but we got 6 elements. That is a contradiction. So, this choice of number of Sylow 2 and 3 subgroups are not possible. Okay. So now let's look at cases by cases. So firstly, case 1. So here N2 is 1 as well as N3 is 1. So, okay. So let's just call them the, like, P is the unique Sylow 2 subgroup and Q is the unique Sylow 3 subgroup. Okay. So clearly they intersect at only identity, because of the cardinality property and because of the order, they are relatively prime order. So this, and both of them are normal because they are unique Sylow subgroup. So you get PQ is equal to G, and that is isomorphic to internal direct product of these two subgroups, right? That is clear. And now, because the order of Q is 3, that means there is only one group of order 3, because it's a prime order. So you get the only possibility is Z modulo 3Z. And for P, there are two possibilities, right? Because it is a group of order 2 square. So either it is cyclic, which is Z modulo 4Z, or it is just the direct product of Z2 and with itself. So you get these two possibilities. So this is by Chinese remainder theorem is isomorphic to Z modulo 12Z, and this is by Chinese remainder theorem is Z modulo 2Z direction Z modulo 6Z. So in this case, you got two groups of order 12. One of them cyclic and both of them are abelian. Okay, so this is case number one. Now, uh, let's see the second case. Now, suppose we are in case two. Okay, so suppose here you have, let's see. So next we can choose the number of Sylow 2 subgroups is say 1 and number of Sylow 3 subgroups are 4. So here this and in 3 is 4. Okay. So you have 4 Sylow 3 subgroups. Let me just call them by Q1, Q2, Q3 and Q4. That is a set of all Sylow 3 subgroups. And because the Sylow second theorem ensures that all of them must be conjugate to each other. So I can induce an action. Let's just call this set as S3, denoting the Sylow 3 subgroup. So we can add G on this S3. Or the notation was can be ambiguous. Let me just call it S. So I can add G on S through conjugation, and there is a transitive action. And so it induces a action or a homomorphism from G to S4. Let me just call it 5. And this is a transitive action first. And now let's see the kernel of this action. So kernel means what? That if G is in kernel of this map, that means G QI G inverse is fixing QI, right? So this is this, and this should hold for all I. That means G is in the normalizer of all those QIs, right? That is first observation. And now from Sylow written there G. So from Sylow third theorem, you know index of that normalizer is the number of Sylow 3 subgroup, right? So this is here 4, and you get this is 3 then, since order of G is 12. So this is same as order of Qi, but Qi is contained in its like Qi is contained in normalizer of Qi, that is obvious, and both of them have the same number of elements. So both of them has to be equal, right? So you get that G belongs to from here you get intersection of all those Sylow, and that is just the identity element because all the Sylow subgroups intersect only at identity. So you get that this action is actually faithful, or this homomorphism is injective. So G injects into S4. Oh, now let's see what we can do. So suppose now, so P was the unique Sylow. Let me just call P as the unique. P belongs to the set of Sylow 2 subgroups of this, and P was the unique Sylow 2 subgroup of order 4. So there are two choices for P. Either it is cyclic or it is direct sum of two cyclic. So let's see the first one. So suppose P is isomorphic to uh, Z modulo 4Z. Okay. Uh, but then you can easily observe that again you will get one of those two abelian groups that you already got in the first case. That I think I can leave it to you as an exercise. You can show it that if P is the cyclic group, then you will not get anything new information, right? So maybe I can leave it to you. And if, let's see, suppose P is just Z2 cross Z2, Z2 direct sum Z2, then you can see that, so from here, because this is an injection, so G must be isomorphic to its image under phi, which is inside S4, and this is a subgroup of order 12. Okay, so I'm leaving this case to you to show that G is abelian. Okay, and now then, so let's see. So now G has 8 elements of order 3 from this condition, right? And so the image of G will again have 8 elements of order 3, right? Because image is actually isomorphic to the group itself. Okay. So now, because G has 8 elements of order 3 and inside S4, there are exactly 8 such elements of order 3, right? Because any elements of order 3 inside S4 will look like some 3 cycles. That is the only possibility. And there are 8 of those 3 cycles that you can calculate from. I think because there are, I think it will be something like this, right? So it is 24 by 3, that is 8. So you get that this image of G has all the 3 cycles in S4. So and you know that this A4 or the alternating group inside S4 is generated by all those 3 cycles. So you get that A4 must be inside this image. But again, both of them have order 12. So you get this inclusion cannot be proper, or the image must be same as A4. And from here you get the G, which is isomorphic to its image under phi, so that is A4. So that is our first non-abelian group of order 12. Okay, so from this case, if P is Z4, then you can show that G is abelian. And if P is Z2 cross Z2, then you can show that uh, G is isomorphic to the alternating group on 4 elements. Okay. Now let's come to the last case, the case 3. So this is case 3. So here we have 3 Sylow 2 subgroups and exactly 1 Sylow 3 sub. Okay, so let's do it. And how will you do it? So look, again, suppose P is that unique Sylow 3 subgroup, and let's just take any other Sylow 2 subgroup. So P was the unique Sylow 3, and we pick any say Q. Okay. So then clearly P is normal inside G, that is obvious. So then we can invoke the notion of semi-direct product, right? Because we have already, like we have one of the subgroups to be normal because P is unique, Sylow, so P is normal inside G. And then you can invoke semi-direct product. And now see, so semi-direct products we need to take Q to the automorphism of P, right? And so this is homomorphism, right? So in semi-direct product we do this, and because P is a group of order 3, there are exactly two possible homomorphisms. One is the identity homomorphism, another one is inversion, right? So ought P, that you can easily show from this that any automorphism can be determined by where the automorphism is the generated. So there are only two possibilities. Either it is identity or it is the inversion. Inversion means every element X must go to its inverse or its square equivalent because these are order 3 elements. Okay. So there are two choices for phi. And you know in a semi-direct product, if you take this automorphism to be identity, then you will again get the usual direct product, right? So there is nothing new because usual direct product again will lead you to those two abelian cases that we have already talked about in the first case. So let's not bother about those two maps or those two classification groups. So let's see. Now again, so first case, if P is say if Q is, so P is fixed. So suppose Q is Z modulo 4Z, the cyclic. Then uh, you can write it as the generator and in this way that suppose Q is generated by X, or let's say, okay, let me take X, and suppose P is generated by Y. Let me write it. So maybe I should change this map, otherwise it is confusing. So here, these are the two possible, and we are taking this one because this will again leads us to abelian cases because it will be again the usual direct product. So you get G is generated by two elements X and Y, where X has order 4, Y has order 3, and so P was normal subgroup, right? So you get X Y X inverse must be. So there are two possibilities. Either it is again Y if we take identity, but we are not taking this, we will take Y square. So this. So again, this is a non-abelian group of order 12. Again, non-abelian, right? And now, if you take Q to be Z mod 2 cross Z mod 2, then suppose say Q is generated by X and W. Okay. Then you get that, then you can write the presentation of Q in this way that Q is then generated by two elements this such that both square is 1 and they commute. That is the usual representation in generator form for Z mod 2 cross Z mod 2. And then you can easily produce an element of order 6 by this P and Q. So P was this say cyclic group of order 4. Oh, I'm sorry, the or cyclic group of order 3. Sorry. So you can easily produce an element of order say 6 here because you take any element of order 2 and an element of order say 3. Let's do it. So and here again the possibility is what you have x y x inverse to be equal to y square. Right? Okay. So I think it's not very difficult to let's just take this element. Let's take W and so I think you can show that this element I think will have order 6 and so eventually what you get let me write it first. So you will get if you just call this element by some other name or maybe you can call it as Z and you have this X as order 2 so you can just write it in this way this such that one of them has order 6 one of them has order 2 and or maybe the most conventional rotation you can write it as the rotation and reflection. So this has order 6. If we just call this element R. S has order 2 and this is the relation. SR S inverse will go to R square. Or uh, let me check. So you get that. So okay. or maybe let's see what we do. So and I'm taking S to be the element W. So that should be understood from the context. And this will be actually isomorphic to the D6, right? Where D6, I am denoting it by like the order, group of order 12. Some books write it as D28, so I'm not writing that. This is D6, is just generated by two elements. One of them is order 6, one of them is order 2, and this is just this, right? You can easily show it, I think, from the above relations. If you take this and you take S to be, uh, say, this is R, and maybe you can take S to be this. I think this will work. You can check it. So eventually, what we get? We get total, so five groups, right? This is these are the first two. This is non-abelian, and this is another non-abelian, and this is the final. So you get total five: two abelian and three non-abelian. And these are all groups, right? Because there are only these many possibilities for the homomorphism of five. So eventually we get total five groups of order 12 by just using the semi-direct proof carefully and the Sylow the three subgroup, three theorems of Sylow. Okay, so now that is all about groups of order 12. So I left two things actually. I left this case to show, and also I left here. It will be just a bit of calculation, so you can do it. So eventually, what you get from here, you will get that the G is just the generated by say X, W, and Y, right? Where order of Y is 3, order of X and W is at 2, X and W commute, and then you need that homomorphism condition from this phi, and that will just give you that X by X inverse will be Y. Right? So that is this condition. And so, like, I think you can again these both two representations are same because if you just change it, like use some change of uh, notation like this, some substitution and all, I think you will get this. So all in all, we get five groups, five non-isomorphic groups of order 12. So that's about it. Now, let me just talk about briefly about say groups of order 30. Let's see how far you can go using Sylow theory in a group of order. So first, my first claim is a group of order 30 cannot be simple. And by simple, I mean it has no normal subgroup apart from those two trivial ones, or the trivial one and the whole group. Oh, so now uh, let's see. So this is the claim. So groups of order 30. Okay. So again, by the Sylow theorems, you get this is 2 times 3 times 4. So the Sylow 5 subgroups, the number of Sylow 5 subgroups has only two choices, 1 or 6. The number of Sylow 3 subgroups has, let's see how many choices. Either it is 1 or 10, right? That, uh, that is easy. And now again, like, so we need to show that none of them, like if one of them is 1, so that means that Sylow T subgroup is normal. But we are claiming, so we need to show that uh, this case, uh, cannot occur. Okay. So if we can show this, then any of the other cases you will get a normal subgroup, a proper non-trivial normal subgroup, and hence G is not simple. Okay, so again the argument will be like the last one, the one we saw using cardinality and all. So again, this will guarantee us number of elements of order 5 are 24 because each will contribute 4 of those or elements of order 5 and there are 6 subgroups. So you get there are 24 elements. And again from here you get number of, that is easy, elements of order 3 is again you get 2 elements from each group. There are 10 groups, so you get 20. And all in all, this is just, if you add, there are 44 elements, which is absurd because the group is 30 elements. So this case is not possible. And in any other case, you will get G is uh, G has a normal subgroup because G has that unique Sylow 3 or Sylow 5 subgroup. Okay. So in any case, so let's just see. So suppose P is the unique Sylow 3 or 5 subgroup. So without loss of generality, so P is the unique Sylow subgroup. I'm taking this. Okay. And let Q be another Sylow uh, 5 subgroup. So P is normal. So that means PQ will be a subgroup of G, right? So you get that this an order of PQ is what? It is 15. So that falls into that category of subgroup where it is the order of that group is product of two distinct primes, where the smaller prime, which is 3 here, does not divide 5 minus 1. So PQ must be isomorphic to Z modulo 15Z, right? And moreover, because PQ has index 2, so it is normal inside G. Okay. So now you can again invoke the semi-direct products, and I will come to it later. So I think there are exactly 4 up to isomorphism. There are 4 groups of order 30. Yeah. So that I think you can easily it will not be very difficult to show from here because what you need a homomorphism from because this is order 15, so you need to take homomorphisms from Z modulo 2 to the automorphism of this PQ, right? Which is Z modulo 15, and this group has order how many? This is phi of 15, right? But again, phi means the Euler phi function here, so I'm again confusing the notations. So this is Euler phi function, this is 8. So this group has, this is a cyclic group of order 8, right? So I think you can do it from here, and there will be 4 up to isomorphism, like there are 4 non-isomorphic groups of order 8. Okay. So now, uh, so here I first claimed that the group is not a simple group, right? So now coming to simplicity, uh, in the next, like in this video and also in the next video, I will talk completely about groups of order 60. So now the primary question is, what is an example of a simple group? The primary question, because so far we have not seen any group of like we have not seen any simple group. Of course, apart from those group which has the prime orders. So of course, in that case, the only possibility due to Lagrange's theorem, they have to be simple groups. So I'm excluding them. So far, apart from those groups of prime order, we have not seen any simple group, right? Because any like we saw that group of order 12 is non-simple, and also here the groups of order 30 is not simple. So uh, the theorem is that firstly let's see an example of a simple group. Okay. So let me just uh, state the main theorem or the main goal for the next one video, this video. So that is uh, A5 is a simple group. First, if I simple group of order 60, right? This is a simple group, and it is the unique simple group of order 60. If you take any other simple group of that order, it will be again isomorphic to this. Okay, this is the main theorem. And this is the first instance, or in other words, this is the smallest order for which you have such a simple group. You can easily see from, like, if you take any group that has order less than 60, that cannot be simple, excluding the cases where the order is prime, of course. That you can easily see. Okay, so far, so let's see. So in this video, I will only uh, consider this case. In the next video, I will talk about the uniqueness. Okay, so firstly, what is A5? A5 is just all those even permutation on S5 from S5, right? So it has order exactly half of the elements of order, exactly half of the elements of S5. So that has 120 by 260 elements. Okay, and now, so let's see the class equation first. Okay, so the possibilities are what? So in a S5, there are 5 cycles, right? This is such a representation. There are, so this is corresponding to 5 plus 0. This will have this, 3 plus 2 will be like this, and there are also 3 plus 1 plus 1, which is just this. I'm not writing the one cycle because there's the usual notation. Or you can take this, these are just mm, okay. Or you can write this, which is just this, and there is the identity. Okay. Now among all these, let's see which of them can be inside A5. So this is this. This is not possible. Again, this is not possible. This is, and again this. So and also the identity. So four of them are possible. And you know that in SN, the elements of same cycle representation are conjugate, right? So they belong to the same conjugacy class. So there are exactly, so we have got four types of such elements, right? Four such cycle decomposition inside A5, namely the 5 cycle, the 3 plus 1 cycles, the 2 2 1 cycles, and the identity. Oh, good. So now, uh, let's see how we can decompose this order 60 into these class equations. So firstly, uh, there is a lemma that will do our job pretty easily. So what is this lemma saying? It says that, suppose you have an element of, say, so you can easily see the class equation for S5 is really easy to find. But the only thing here to consider is like all those classes will be inside A5 or not. That is the main question. Like, for example, if you take the class with representative this 5 cycle, the question is whether all of that class belong to A5 or all of that, or there are some element which is not inside A5. There is some odd permutation. That is the main question, right? Once you are able to answer that question, then the rest of the things are very easy. Okay, so here is the lemma that is doing exactly what we need. So suppose for some element X, the stabilizer inside S5. So here I'm talking about S5. So if this is completely inside A5, if this happens, then this orbit of X in A5 is splitting into two halves. Oh, and if so, there are two choices. Either the stabilizer of X in S5 is inside A5 or it is not. And in this case, the orbit remains the same whether you are in S5 or A5. Okay. So now, uh, let's see how can apply that lemma. I will come to it proof, come to the proof later. So, for example, let's just take this element, say the element 1, 2, 3. Okay. Here you can see this commutes with 1, 2, 3, right? Because this is a product of disjoint cycle. And so you get 4, 5 is, and remember this is not inside A5, right? So, and this belongs to the stabilizer. Sorry, stabilizer of 1, 2, 3 inside S1. So, we are at case 2. And so orbit of that element will be same as orbit of that element inside the whole group. It's 5. So, and how many such conjugates can it have? So here the decomposition cycle is of that form. So you can see that this is 3 to the power 1. There is the usual formula 1 square times 2 factorial, which is just uh, 20, right? Okay, so that is from here 20. Now let's see the second part, this 2 to 1. And then again take just this. So, and because this will cancel out, and because this is in self inverse, and again they are commuting. So you get 1, 2 is such a stabilizer. And again we are at case 2 because 1, 2 is an odd permutation. So you get that again here the orbit, this the orbit of this element 1, 2, 3, 4, the 2 cycles does not split if you go inside A5. And so how many of them are possible? Again, the usual formula. So this is 120 by 8, 15. Okay. And clearly this is 1, that is obvious. So how many elements are left? So there are, oh, no, this is 20. So there are 24 elements, right, for that, the first choice, the 5 cycles. So there are two cases. There are two choices. Either it remains 24 or it will split into two halves from the first one. So let's see. And so that can be easily seen from one thing that if so there are two possibilities, right? Either it is 24 or it is 12 plus 12. But from the orbit stabilizer theorem, if this is 24, then we are inside A5 now, right? We are doing inside in A5. So order of that orbit should divide the order of the group. So here the orbit has order 24, and clearly that does not divide 60, right? So that possibility is ruled out. So the possibility is it actually does split, and hence we got that class equation for A5. We get the class equation for A5, and that is 60. It is 1 for the identity, and if I just write it in increasing way, that will be here you get those two 12s, and you get 15 plus 2. So this is the class equation of A5. Now the rest of the things are routine. So we need to show that A5 is normal, right? Sorry, A5 is simple. So that's a general thing. You can, I think, all of you know, all of you have observed when I was discussing those group actions. Suppose you have a normal subgroup. Okay, so you have a normal subgroup in any group. Let's be general here. Let's not take. So this is some observation or remark you can take. So suppose N is a normal subgroup. Then given any G inside N, the entire orbit of G, which is just right in group action sense, because here the action is by conjugation. This is inside N again, right? Because N is normal. And again, if this like this takes all the elements of N, you are done. And if not, you can take again. say if, let me write it here. So if this is not all of n, so you can take any h from the remaining elements and again consider orbit of h, right? And because orbits are either same or distinct, so you can show that n is actually union of disjoint union of such orbits, right? And so this is if n is normal. And now, what does it actually say? It says that suppose we have a bigger group. For example, here the bigger group is A5, and we are interested in any. We're interested to see if there is any non-trivial proper normal circle. So, if that is the case, then in that case also n will be like union of some of these orbits, right? These are all the cardinality of those orbits, right? So there will be some subcollection of those elements. Let me write it clearly here. So suppose you have this set. Okay. So if there is a normal subgroup, non-trivial proper, then order of that normal subgroup will be sum of some subsets of S, right? That is the easiest way to define it. So there will be some subcollection of this set S, or maybe let me put 12 again here because there are two 12. So let's not get confused with the usual way. So all I'm saying is if n is a normal subgroup, then the order of n can be written as some subcollection of sum of these elements. For example, like we are talking about sum of this one, where one of those elements can be taken exactly once, right? For example, this, or for example, this. I'm talking about this type of sums, and n should be some of like some form of this kind. The order of n can be written in some form of all these possibilities. And because n of course has the identity element, the element 1 has to be there. Okay. So this, and let's take, or let me just exclude 1 from here. So let's just take this plus this. Yeah. So that should be the best way. And anyway, don't get confused with the notations and all. All I'm saying is that order of n should be uh, written as sum of uh, these 5 possible classes, right? Because n is normal. And now it is routine because what are the possibilities of any subgroup of order 60? Right? So there are possibilities of either it is, of course, you are excluding the trivial case, so it is 2, 3, 4, 5, 6, 10, 12, and then 15, 20, and 30, and we are also excluding the entire group. So then now there are these possibilities, and also we need to have this order of n should be 1 plus summation of these kinds, and you can easily see none of them can be written as sum of these two 12s, 15 and 20. That is easy because so of course clearly all of them are bigger than this, all of these cases. But I'm excluding 12 because here is already one extra. So the minimum such sum can be at least 30. So these are out. And again, 15 cannot be written, right? Because we need to take one also. So this will be like this. And of course, you can't get 14 from this type of sums, right? So that is also not case. That is also not possible. Similarly for 20, because for 20 you get 1 plus 19. And again, 19 is not possible to write as some of these elements. So that is also ruled out, and similarly 30 also. So you get that A5 is simple. Okay. So that is an example of a simple having order, not a prime. And in the next video now, I will talk about the uniqueness, and that will also begin be like it will be a long video because there is a small part we need to talk about certain things, but all of them will be very elementary, and only you need to use these three Sylow theorems and nothing else. And even in this proof, I have not used anything other than the basic class equation for S5. Oh, I forgot to prove the lemma. Sorry. Okay, so let me just prove that lemma. And the lemma is also immediate. In fact. Let's see. So I can write it here. So proof. Okay, so if this is the case, if we are in case 1, then stabilizer of x inside A5 is that is in S5 intersection all those elements inside A5. And because of that property, you get this is actually this. And that is again immediate because of the orbit stabilizer theorem. This is the orbit which is A5 by stabilizer of x in A5. But that is same as stabilizer of x in S5. And now, right? Sorry, this is by 2. And this is just half times again using orbit stabilizer theorem. This is orbit of x inside this. Right? This is the first proof. And the second one is similar. So if this stabilizer is not completely inside A5, then this stabilizer of A5 of X, this is again a subgroup of this, and clearly this is index 2. Because you can again compose it with the sign permutation and all. I'm not going there again. This is the usual proof of that there exists exactly. There is either no odd permutation or there is only half odd permutation. So I'm just using this in the index this in this notation. So again, that is so you get that orbit of this inside F5 is order of F5 modulo the stabilizer of X, and then this is this by 2, and from this relation you get that from this relation what you get is uh, this is again stabilizer of X is 5. Right. So this 2 cancels and this is right. So that was the proof. So almost forgot to. Okay. So this is all about these important because yeah. Anyway, so the next time I will talk about the second part of this proof, that is the uniqueness. That will be again an interesting proof. There will be some small details, and I will not use anything other than what we have proved so far in the last 6 to 7 videos. So yeah, let me stop it here.